Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
All right. Well, good morning, good afternoon, good evening to everybody joining us for this DSIAC webinar. My name is Brian Benish, and we're happy to have you today for this webinar. I'm going to go ahead and flip to the presentation here. And as I'm doing so, I just want to make everyone aware of a couple features of the webinar, the WebEx platform. First of all, I want to make you aware, if you are in the WebEx platform, that there is a Q&A portion. If you don't see it immediately, it should be accessible by clicking the ellipses, 3 dots next to the chat, perhaps, and you should see Q&A. At any time during the webinar presentation, if you have a question, please go ahead and type it in and submit it. At the end of the presentation, we're going to have a little Q&A section where we'll just go through the questions in the order that they are received. But again, I do want to distinguish that from the chat. So if you have a question, please try to get it into the Q&A portion instead of the chat. For anybody who runs into any technical difficulties during the presentation, first off, you can access the slides from the webinar webpage, which we'll post in the chat in a few moments. But also rest assured that this is being recorded, and so we will get the recording available and sent out to be rewatched if you do have any technical issues. I think that covers the bases. Again, if you have any other questions or curiosities about DSIAC, please go to the website, poke around, learn more about who we are and what we do. As a way of introduction for our presentation, we're happy to have Zhenhua Jiang with us. He's a principal research engineer with UDRI, the University of Dayton Research Institute. And his research interests include machine learning, autonomy, predictive analysis, analytics and control, microgrids, probabilistic modeling, and quantum computing. He has developed a data-driven, physics-guided Bayesian neural learning method that is well-suited for modeling, control and optimization of various energy systems, autonomous air, space, ground, underwater vehicles, and quantum systems. He has over 100 publications and several patents on subjects such as distribution automation, model predictive control, probabilistic decision engine, and quantum probabilistic solvers. He has a PhD in electrical engineering from the University of South Carolina, and we are very happy to have him with us to give this presentation. And so, Zhenhua, I will go ahead and mute myself and hand the mic over to you for the presentation. The floor is yours.
Okay, thank you so much, Brian, for your nice introduction. Good morning, good afternoon, everybody, depending on where you are. My name is Zhenhua Jiang. I'm with the University of Dayton Research Institute, UDRI. Today, I'm going to present a topic on emerging applications of machine learning and predictive analytics in naval energy autonomy. This presentation is primarily based on a DSIAC journal article with the same title, co-authored with Scott Meter from Naval Facility Engineering, Naval Fac, and David Dunn at UDRI, and some other relevant publications. This slide shows a brief outline of the presentation. First, I will talk a little bit about the background and challenges in modeling and control of energy systems. as well as the driving force for the US Navy to use machine learning and predictive analytics. Then I will elaborate on the feature of a machine learning analytic solution and discuss the control solution based on the machine learning and model predictive control for autonomous energy systems. After that, we will go through some applications of machine learning methods for level energy systems and briefly touch on the anticipated benefits and recommendations for some future development. Finally, I will conclude the presentation with some outlook thoughts. Now let's talk a little bit about the background. During the past few decades, US Navy facilities have contributed a considerable fraction to the total energy consumption in the defense sector. To reduce energy cost of those facilities, there have been a series of research and development programs dedicated to distributed renewable energy storage and energy efficiency technologies. Within the Department of Defense, installation energy typically addresses the power control and optimization problems at the components level. Typically, we talk about the generator controllers, solar inverter controllers, battery controllers, etc. With the advances in the sensor technologies, it's possible to install many cost-effective sensors in distributed power plants and node centers, and connect and visualize the big data for hundreds or even thousands of parameters and variables. An important question is coming up. How could we use those large data sets to help improve energy utilization efficiency and reduce energy costs? Due to the complex energy flow processes, it's necessary to determine what parameters or variables are more important or effective than others in generating energy savings. So it's also desirable to figure out how these factors could be managed to optimize the operation before real benefit can be achieved. So this presentation attempts to discuss some options to answer those questions. In the past, some solutions such as microgrids could provide improved resiliencies, but the challenges are still existing, and some new capabilities are needed. For example, we may want to have some system-wide energy optimization across the large-scale power grid, or we also want to have some real-time look-forward prediction capabilities to understand the system behavior, such as the renewable energy availability, load profiles or priority, load costs, or even electricity prices. In the case of parallel operation, multiple generators can operate at full or partial capacities, which can result in some varying fuel efficiencies. Also, these generators may need to adapt to different control scenarios, for example, the voltage regulation or active power regulation. We can use some node sharing strategies, but it might be based on some dynamic priority level, which depends on the scenarios or operating conditions. So some additional data analytics or learning algorithm might be desirable. So with all of this said, situational awareness about the system operations, such as generation and node, might be essential to achieve more efficient utilization of all grid assets. However, traditional control systems may not address all of these factors effectively, particularly in real-time operation. So to address all of these challenges, it's very important to understand options and the impact of potential energy-saving technologies, and even automate the energy-saving processes. Specifically, to answer the data analytic questions raised earlier, the UDRI team proposed a machine learning and predictive analytics solution in a contract with the Naval. This solution combines the benefits of the data-driven Bayesian neural network with a physical guided learning framework. And this solution can also enhance the predictive capabilities to optimize the control for microgrid operation. And the objectives are to improve the energy forecasting accuracy, reduce energy costs across the Navy shore deployment, and also reduce the redundant equipment if possible. So now let's take a look at some innovative features of the machine learning analytics solution we are developing. In the past, modeling and simulation of dynamic systems have been an important tool for control system analysis, design, and testing. Traditional physical-based models provide very high fidelity dynamics for the control design, but it's still facing challenges. There might be some unknown system dynamics at the time of design, and also the system or model parameters may change with the system operating conditions. So on the other side, some data-driven machine learning methods may analyze the data and extract some useful insight. These analyticals might be available because we can take advantage of the operating data available from sensors and some machine learning algorithms and computing resources. But on the other side, the machine learning approach typically generates some point-to-point predictions, but the uncertainty in the causal relationship may not be fully captured. What is good is that some probabilistic-based Bayesian learning may have to concisely capture uncertainty based on the probability. So the Bayesian inference typically assumes some prior knowledge based on the prior probability distribution and can derive the posterior distribution or some new knowledge from the connected datasets. This dataset can be considered as the new evidence or observations. And the Bayesian inference process can update the belief or the behavior of the prediction. So our approach is a combination of all of the three aspects. So the physical and machine learning models can generate point-to-point prediction, but at the same time, the Bayesian inference can update the probability distribution of the parameters across a wider operation range. So here, this shows a diagram of our approach, where many people talk about cyber-physical systems or digital twins. Our methodology is a three-pronged approach. Here we consider the physical, digital, and probabilistic aspect. So this is a three-dimension, or we call it a triplet framework for system dynamics modeling and learning. In the physical domain, sensors can collect data from physical systems, and the actuator can perform commands sent from the embedded controllers. Physical-based equations can be used to characterize the temperature dependency and the dynamics in the physical systems. In the digital domain, machine learning methods can capture the causal relationship and reflect the input-output relationship in the training datasets. High-performance computing systems such as GPUs, FPGAs, or supercomputers can help to accelerate model learning processes. Uniquely, the third dimension in our approach is a probabilistic representation and analytics, which can quantify uncertainty and capture the stochastic behaviors and consequences. This is important and useful for what-if scenario analysis in contingency studies. It will provide opportunity to maintain some deep deliberations about the possibility that has not been happening yet and predict the potential consequence before adverse effects occur. However, this is very computational expense. And the good thing is that the challenging probabilistic computing in the belief space can be implemented or accelerated by some emerging quantum computing hardware. We are currently working on a very interesting quantum machine learning project under a contract with DARPA that may also help to address some probability-related issues for energy system. So our machine learning analytics solution has three dimensions and leverage a modeling method suited to different domains, including the physical domain, digital domain, and the probabilistic domain. In this framework, the physical space models can represent the known knowledge we have that can be integrated into the design of a neural network. The neural network learning capability can learn the patterns or features from the operational data and predict the potential behavior of the system. And the Bayesian inference can be used to capture the uncertainty and the probability distribution of the variables or factors in the model. And altogether, this can achieve the more insight about the system operation. So this diagram illustrates an example of the model integration or fusion process of data-driven physical guided Bayesian neural learning. So before the design, we may need to determine the existing unknown equations about the system model and some parameters and constraints of system. So this model integration process consists of 6 steps. first we can formulate the physical basic equations and feed these to the design of neural learnable model. And the second, we can use the offline or online data sets to train the neural network models. And in third step, the Bayesian inference can be used to generate the probability distribution of the model parameters. And then we can combine the physical-based model equations with the neural network models and probability distribution of the weights all together into the integrated format. And in the next step, so we can do some sampling based on the probability distribution to generate discrete time state space equations that the engineers can understand. And finally, we can use the model for the prediction and including in some control loops. This is shown an example of the neural network model. So it's called a short-term memory neural network, which is subset of recurrent neural networks. So this type of networks consider some internal or some additional stored states resulting from the past output. And this internal states can be considered as a memory from the past, and it can be internally controlled. So the different gates here can be designed to control the information flow in this type of network. We have input, we have output, and also the past information can be used to generate the new output. So these three data gates are used to control the information flow. And this project is similar to a valve to controlling some water flow in a water distribution system, or a power controller controlling the power flow in a power grid. So the forget gate here determines which data could be forget or removed from the information flow. Or the input gate can determine which data from the current input or previous output will be fed into the state update module. Output gate will determine what data, which information will be used to update the output. So those three gates can control the information flow in the model, and we can decide how much will be forgot or how much will be used to generate the new information. This shows a diagram for the long short-term memory network that can be used to model the time sequences for time series prediction. There are three main layers. So the input layer can handle the data preparation process, such as reading data from data files, receiving data from memory blocks, normalizing data, and selecting input features in the data sets. The heart of the network is an RSTM layer that consists of multiple cells, processing the input data sets in a desirable manner. Here in this layer, one cell can feed the next cell or the following cell. N cell, RSTM cells can be connected together to create a series. And this length can change depending on the anticipated prediction algorithm. And then the output from each cell will be used to drive output layer. It's typically a four connected neural network. So this network can capture the information about the system or dynamics during a time period, for example, one minute or even longer. This diagram shows the structure of one particular cell. So each cell has three gates, as we mentioned, and the input information will be updated to generate the control signal for the state update mechanism, and the state output will be also be managed to generate the control information. And here there are different equations to describe or characterize different gates, and those equations have some parameters, and the parameters will be learned from the operational data. So the goal to train the model is to learn all different weights and bias in the simulation in the equations. Next. So after designing the machine learning models and the algorithms to train the model, we can take some realistic data sets to train the model. So we use the power production data from a real solar power plant on University of Dayton campus So we collect the data to train the model and consider the training data sets. And here on the left, we have a figure that shows the loss function in the training process. And we can see that initially there's a very quick jump in the cost function, but it can reduce to less than 0.1% within 30 epochs, basically. And we can consider that the model will be trained enough because the loss function could be acceptable, or if there's more change in the model update. After we train the model, we can use the validation data sets to make predictions. But the idea here is that take the learned weights, the parameters in the model, and we use the machine learning neural model to predict what could happen based on the new conditions. And here on the right-hand side, the graph shows the predicted solar power generation with in comparison with the actual measurement. So we can see that they're pretty close. But here the thing is, the bigger assumption is that we use the solar irradiance as the input or feature in the learning model, and then that information will play a very important role in predicting the solar production. And this also shows that it might be very important to install the sensors to measure or to predict the solar irradiance, and that is related to the first question we discussed. How we can use the data from the sensors to make useful prediction. So this says that the sensor data will be important. We may select the most important parameters or variables to measure. Let's take a look at the control solution based on the machine learning and model predictive control. Our solution is a integrated machine learning driven model predictive control. And we use the advanced model predictive control to optimize energy management and also to dynamically manage power flow. So in this control scheme, models can be based on the physical knowledge long on the time of design or real-time machine learning models during operation. The human intelligence typically works in 4 steps: sense, learn, predict, and optimize. We will take this human learning mechanism as a design guide for our solution. For example, in this system shown in the diagram, that we can use sensors to collect data from different components, such as generators or load, and analyze the data to learn models to capture the components' dynamics. And then we can use the models to predict what could happen in power generation or consumption in the near future, and finally include the model prediction in our optimization algorithms and generate optimal control actions. So there are 3 closed loops in the system. Here, the inner closed loop here is using the model prediction and compare with the measurement data to update the model parameters. So this model is to calibrate the model online. And the second closed loop is to optimize the power optimization. Basically, we can consider the very fast power dynamics. And the outer closed loop is considered the system-wide energy optimization. Their value to the DoD customer includes the improved efficiency from different energy resources, improve the resilience of the entire power systems, and reduce the cost in energy generation and delivery. There are some advantages over other solutions. For example, improve the situational awareness due to the learned models. Also, the consideration of operational constraints in the closed loop control. And also the system can consider the optimization of energy flow and power flow individually. This is an example for a hybrid power system. We can consider the 2-layer of model predictive control for energy optimization and power management. So this system is a typical like power propulsion systems that may happen in the facility systems, or even like a shipboard power systems or aircraft power systems. There are some major power sources and auxiliary power sources and energy storage systems, and all of the measurement can be connected and sent to the controller through the secure communication link. And the controller consists of different different hardware equipment. So the host computer can set up some parameters, and real-time processor can handle the computing for the energy optimization. And some advanced processors like FPGA, field programmable power gate arrays, can help to accelerate the fast control loop for the power dynamic power management. So this system can decouple the energy optimization from power management. So we'll take the simple circuit as an example to show how we can design the two-layer MPC. So first, we formulate we follow a general approach to formulate the model predictive control schemes. So typically, we need to know the models of the dynamic system. The models could be based on the physical knowledge or equations, or even the machine learning models. And we can consider some constraints on the control variables or even state variables. And the first step is to define some objective function we're trying to minimize or optimize. So that typically consists of some objectives like the energy consumption reduction or energy cost reduction. And the next, then we can discretize the equations and also consider some constraints in equality constraints. And all of this together will be integrated into expression called the Lagrangian equations. So this Lagrangian equation will consider the objective functions, some equality constraints, and the inequality constraints. So the next step is to solve, to minimize the Lagrangian. So in order to do that, we can define a decision variable vector theta here. The goal is to find the best decision vector theta so that the Lagrangian could be minimized. According to the first order optimality conditions or KKT condition. So at the condition that the derivative of the Lagrangian with respect to the decision vector theta is 0, then the Lagrangian will be minimized. So the goal then is to find the solution to this equation, and this is a nonlinear equation of theta. So by using the Newton's approach, we can find the iterative solution of the decision vector theta according to the equations shown here. So there are some calculations to find the like called the Jacobian matrix or gradient vector to update the decision vectors. And after some iterations, so the decision vectors could be found. And this process will generate the optimal control loop for the control systems. Next, I would like to take a very simple example to show how we can apply the model predictive control to the hybrid systems. So here, there are two MPC controllers here. The higher MPC is trying to optimize the energy flow across the entire system, and the lower MPC is trying to manage the dynamics of the power flow. First, in order to optimize the energy flow, so we can consider the model equations. Here we can find the energy flow equations for different components. For example, the main power sources, the ancillary power sources, and any storage systems. And all of these equations could be discretized to describe the relationship between the input and output variables. And the next step is to define the objective functions. Here we can consider the generation cost, also the energy reserve, some dynamic energy reserve for the energy storage systems, and also the power components may also have some constraint. For example, the power generation capacity and the rate of change of power capacity, and also the energy storage in the capacity of energy storage. So there are different constraints we can consider, and then we can follow the general procedure to develop the control scheme for the higher level MPC. So next step, we can also consider the lower level MPC to manage the power flow. Here, this lower level MPC more focusing on the dynamics or the management of the current flow and voltage regulation. So we can write the dynamic equations for different components such as the inductor and capacitor. And then we can describe the differential equation into the discrete time state space equations. And the next step is to also to define the objective function. So this can consider the current regulation, voltage regulations, and also we can consider the constraints in the control in the actuators like the power converters, the change of the control variables, and also the current from the energy storage systems. So by following the same general procedure, we can then develop the control scheme for the lower level MPC. To demonstrate the operation, we can take a very simple example here. This publication describes the simulation model in MATLAB, but we can consider the implementing the control MPC code in Naval environment. So we can take the lower level MPC as an example. So the model consists of the power supply, power system model here with the primary power sources, secondary power sources, and energy storage systems. And we have different type of loads. So we can have some change in the load, and the two MPC controller can work together. The higher MPC code can generate the set points for different components, and also send the set points to the lower level MPC. A lower level MPC is going to generate control command for the power converters. Here, this shows a few charts that compare the performance of the lower level MPC for power management and in comparison with the PID controller. Traditionally, we can use PID controllers to regulate the current and voltage. Here in this diagram, we can see that there is a step change in the current reference here for the primary power source, and at another time, like 800 milliseconds, we have another step change in the load. So basically, you can see that if you change the set points for the power supply of power flow, then you can see that the MPC can regulate the current smoothly. And in another scenario with the PID controller, we can see that the current will experience some oscillation or some reigning. And particularly when there's load change, so the hybrid power systems is trying to respond to load change, and there's more oscillations here in the current here, and also the voltage will experience some oscillation. But the MPC can help to correlate the power flow and voltage regulation better than the PID controller. So this is just an example to show some of the advantages of the model predictive control strategies. Now let's take a look at some applications of the machine learning methods for lower energy systems. In the solution, we can generate some new modeling and optimization capabilities. So the machine learning model can predict some varying time domain dynamics or probabilistic behavior of the system. And real-time prediction capability can consider the physical dynamics or uncertainty in the systems, or even the causal relationships. And the optimization methodology can consider the optimization in the control loop. So all of these capabilities will help us to produce some new functionality in the power system. So for example, we can learn and validate a compact representation of the physical components from offline operation data. And once we train the model, we can also use the model to make some prediction and update and calibrate the model from the online operation data. And uncertainty can also be incorporated in the model to consider some contingency in the prediction. And the variations in the power production or even load consumption can help to determine the set points for different energy assets. And also the machine learning capability can be used to accelerate the hardware and loop testing of the power systems with some compact learning-based models. Because some models might be very hard to compute, or even some dynamics may not be known. But if we learn the dynamics from the operating data, so the model could be used in hardware and loop testing to accelerate the power system design. We can apply the machine learning methods in different ways. So for utility planning, we can use the predictive analytics to, for example, forecast the renewable energy production, load profiles, or even load priority levels, fuel efficiency for different components such as motors or some other loads. And also, we can use the machine learning-based approach in the facility management, for example, the energy optimization for building energy systems or even hybrid vehicles like hybrid trucks. And also the digital twin could be developed to facilitate the test facility to consider the dynamics from the machine learning models. And also we can leverage the machine learning model prediction capabilities in the predictive maintenance schemes. There are some other applications. For example, in the microgrid domain, you can consider the machine learning capabilities to model the dynamics from renewable generation, variable loads, or even the different utility prices. And also we can use operation optimization in different objectives. For example, if you optimize the energy costs or some power generation loss or deliverable loss, and also we can use this to size the energy storage for stability consideration. And hardware in the loop testing can also benefit to study the resilience of the system under different conditions. Level for the aviation operation energy can also benefit for this type of machine learning and predictive control because there are some safety consideration, weight size considerations, and also the agility or mobility might be a concern because of the control systems may achieve some autonomy from the predictive capability. And the desired advantages may also include predictive optimization in real time, some proactive actions before the operation changes. And also the model predictive control can consider the operational constraints or even safety constraints. Some the operation costs could be reduced by maintaining the optimal dynamic energy reserve. So basically, the energy storage system may be sized to the necessary level that can meet the mission requirements. Also, this type of energy system can benefit the automated operation because of the autonomous learning and prediction capabilities. The proposed technology can also be widely applied to shipboard power systems, particularly electrified ships, because there are diverse energy flows and flexible controls and different type of equipment. For example, there are complex components on board ships. For example, the primary movers, generators, sophisticated loads such as directed energy or high power radar. So those devices may have some operating constraints and they need to be considered in the power supply design. And also there's a need to optimize or minimize the power system size and weight. Also, optimized operation of propulsion power systems can reduce the system weight and size, fuel consumption, and also the total operational cost. So as a whole, so all these AI-driven digital engineering tools can help reduce the development time and cost, acquisition, sustainment, and total ownership cost of all fitted systems. So let's go through some anticipated benefits. So primary benefit that we can expect is to improve the military capabilities due to the enhanced power and energy performance enabled by the AI machine learning technologies. So this could be achieved by capturing energy system dynamics, degradation, and uncertainty into the model and the control design, providing the mechanism for online learning capabilities to update the model to understand the varying conditions. Enabling some fast or even faster than real-time hardware and loop simulation to gain insight of system behaviors. And then finally, empowering the integrated control platform that can proactively manage energy flow among the subsystems. So in order to make the benefit real, some validation is needed in the realistic applications. And this validation efforts may include energy savings, cost savings, and power quality and resilience improvements. So there might be different ways to achieve the goal. A main recommendation for future development will include demonstrating some prototype of the control or the energy controllers and validate their advantages. So including validating the effectiveness and accuracy of machine learning models for forecasting, conducting some power hardware and loop testing of a prototype in some realistic microgrids, and performing the field demonstration at DOE installation site for rapid transition. For further development, the machine learning method can be used in the test and evaluation stage. For example, we can use machine learning for screen and down select some test scenarios in maintenance or some other test facilities. We can also automatically analyze test data to determine the correlation in system parameters and generate some candidates for best design options. And also we can have diagnosis or prognosis or preventive maintenance in some energy systems. So to summarize, we have discussed some emerging applications of AI and machine learning technologies in lower level energy autonomy and digital transportation. And this can achieve potential impact on operational autonomy and the benefits across the DOE's power and energy ecosystems. So an important note is that we can also amplify the impact of AI and machine learning technologies by combining them with other emerging digital technologies, such as sensor fusion through universal learning, predictive analytics by deep learning or data science methods, optimization techniques, or even emerging quantum computing. So with that said, I conclude my presentation, and thank you for your attention, and I'll be open to questions.
Great, thanks. Thanks for the presentation. Very nice job going through everything. Great time too. So we do have a few questions that came in. First off, let me address a couple top level ones, which is that the reference journal article that was on the cover slide is not yet published. We expect that to be published within the next month or so. You can keep track of that on DSIAC.org under our journals, and just keep an eye out for notification on that. All right, so let's see. First question that came up, actually, in reference to slide 14. So in reference to slide 14, the question was, wait for you to get there maybe.
Yeah.
How far out is the neural network forecasting on slide 14? Is it 1 minute, 2 minutes, 5 minutes, or 24 hours? Something like that.
Okay, yes, thank you. This is a good question. As I said, probably the LSTM network typically consists of multiple cells, and each cell can capture the dynamics in one time instance, and the LSTM network can consider the time sequence. And in this particular example, we can consider 1 minute. It's like 60 samples or 16 points. And because of the sensor data we have with the resolution of 1 second, so basically we have we have data for each second. So basically the 60 samples will be 1 minute. So basically the neural network model will consider the time sequence for 1 minute. And the input required will be the solar irradiance prediction. And that can, because that establishes the correlation between the input and output, because solar irradiance may have a bigger, very major impact on the output of the power production. And the thing that if you have more or higher resolution data, they can have the prediction. If the size, the challenge, it'll be different, because for long-term forecasting might be different than short-term forecasting. There are different challenges. For long-term forecasting, because there are too many variables or too many factors can affect the production. So it's might be a little harder to predict. But for short-term, we may also consider the physical dynamics. If you consider the prediction of solar irradiance, but if we consider take into account the weather condition or even the dynamics of the weather condition, so we can also predict some solar irradiance using the physical model. But this was not considered yet. We only use the historical data for solar irradiance and predicted the solar irradiance to predict the power production.
Got it. Okay. No, that's good. Very good. Thank you.
Yes, I saw one question in the chat box that is also related to the predictive precision. So is that the same question you mentioned?
That might be, yeah. So I was going to.
Oh, yeah, I got it. You said that Bruce said that the question was answered. Okay, thank you.
Right. So did you think you kind of already addressed that question of how good the predictive precision of the combined machine learning approach was?
Oh, yeah, that's the second question. The second question is that any country data side by side comparing the prediction versus the actual. Yes, so this figure here on the right side shows the comparison of the prediction with the actual measurement for a day, basically 24 hours. But here we only cut the daytime, right? So it's 12 hours basically. And we can we can probably show this frame by frame. But this figure doesn't show that one. But there might be a way to compare them and understand the difference between the prediction and the measurement for each time frame, right? For example, every minute. This is something that we could consider in the future. To understand the difference between the prediction and measurement frame by frame, and then characterize the difference. That can also help to improve the model training process, because there might be more or higher errors between or difference between different conditions. If there's a continuous or smooth operating conditions, the error might be small. But if there's rapid changes, particularly in the weather conditions, then power production may also have rapid changes, and that is a very challenging condition to predict.
Gotcha. Okay, no, that's good. One other question kind of came in through the chat here is about the work overall that you're doing. Is this a TRL level 1 or 2? And kind of related to what you just described, have you demonstrated the results with simulations or physical systems in the lab, or other ships or power systems?
Thank you for the question. This is it's also a good question. Because the solution is it's a comprehensive solution. It consists of the model prediction and control, and also different control loops. The entire solution might be at the relatively lower TIR, might be like 4 or 5. Some components, like the prediction package, might be at the higher TIR. For example, the machine learning based prediction for power production has been implemented in the computing hardware, FPGA. That's feed program gate arrays. FPGA can run the computation in parallel and also fast. And the algorithms was implemented on FPGA, and the model was used to predict, like what is shown here in the figure. So the model can be used to predict some production. And this can verify the algorithm to some extent, because of the prediction pretty match the measurement pretty close. But there's some, again, there's some basic assumption is that the solar prediction is available. But here in this case, because we use the historic data to train the model and make the comparison, and some data might be based on the historic data, particularly the solar irradiance. But this solar irradiance prediction is another challenge, because for weather forecasting, there's some prediction for the weather condition, but for the solar irradiance is also another challenge. And that is associated with the power production prediction. And so in that sense, the TR level might be lower, probably the 3 or 4. But there's still opportunities or options to develop some more sophisticated models to predict the solar irradiance or to consider the physical dynamics of the weather condition.
Okay. Well, and while you're on slide 14, the kind of follow on to that was, if you could just clarify, how far in the future does the model generate results?
Oh, you mean the prediction times for the?
Yes.
Since this algorithm or the model had been implemented on the real-time computing hardware, like FPGA. So basically, it will run in real time. The real time means that if you want to predict the production for the next minute, so basically this prediction could happen within 1 minute. It's less than 1 minute. Basically, it can. So the time is real time or faster than real time. So I would think that it depends on the time horizon, right? So if we predict for next second, then it could be immediately available within 1 second, right? But typically we don't consider the second by second prediction. We may consider for a longer time horizon, like a minute or even longer for energy planning, right? So basically, I would say the answer is that it can run in real time and depends on the time horizon we want to consider. It could be longer, it could be shorter. But the algorithm can run faster if the model has been trained. And the prediction stage is just to calculate the prediction based on the input features.
Okay, good. Well, and while we're on slide 14, the next question that came in was about that as well. It says, on slide 14, how do you determine when to stop the training of the LSTM model or network? So I ask because the LSTM loss comes down to a small value of 0.001 at 5 epochs, and then increases and finally comes down again to 0.001 at 30. So how do you use a time-based or loss value-based stopping criterion?
Okay, thanks for the question. This is a very this is a good note because we noticed this as well. The thing that at the very beginning here in the first few steps, the training also is basically random. We may have some initial guess, or we get some initial values for some weights or parameters, and if it happen to be good, we can get some good parameters. Then we can reduce. We get a lower cost function. Total cost, but that cost may also bounce back. Okay, we increase because when we train the model, the parameters will be updated according to some policy, right? So basically, the gradient of the cost function. So the parameter will change. It may go to a wrong direction. For example, in search process, that we can see in the middle part, the cost loss function may have some increase, right, in the middle. But eventually, it can reduce. But the point is that we need to determine how good it will be, and based on the experience, so we can define some relative error. For example, if the change to the previous step is pretty small for some time, right? So if within a few time steps, if the relative error is within some range for some time, then we can consider that is good enough, or that it's time to terminate. And this is purely empirical, and that might be a way. If you train a longer time, might be a way to get better parameters. But there's another risk because this type of neural network-based models may have a problem called overfitting. In other words, that if you use the data to train model, the parameters might be good for that data set, but if you overfit the model may not be accurate for other conditions. So that is another problem. And in order to address this issue, so our approach is to consider the probabilistic approach. Basically, it's consider the probability distribution of the weights rather than a single value for different parameters. So then the model may have some range, right? So we can predict it's like the weather forecasting. We consider the different conditions with different probability or confidence level, right? So that may be another a future direction to go. We can consider the probabilistic prediction rather than point-to-point prediction.
Mm-hmm. Good. Thank you for that. Okay. I think we're just about out of questions as far as I can tell. If there's any final questions, I'll speak for a moment so if somebody can kind of get them into queue. But if not, as a reminder, we'll make this available, this whole presentation available on the website as the slides already are. And if there are any questions, follow-on questions, it can either be directed to DSIAC, and we'd be happy to help field them and send that over to Zhenhua for some help or for insights on that. But you're welcome to also, I'm sure, reach out to him for anything else you might have. So I think with that, we'll go ahead and wrap it up for this webinar presentation. So thank you all for hanging with us the whole time, and thank you, Zhenhua, for the presentation and answering all the questions. You did a fantastic job, so appreciate it.
Thank you so much. Thank you, Brian. Thank you, everybody.
Of course. Yep. Have a great rest of your day, everyone. Take care.
You too. Bye.